Hello, welcome to today's seminar. Today's speaker is Zdeněk Dvořák. We will be talking about Threechoosability of planar graphs of girth 5 and will establish the superiority of discharging again. And you will be speaking about joint work with Bonamy, Kardos, and Postle.
Okay, thank you for the introduction. Okay, so let's start with some motivation. So we know that there is the famous four-color theorem. So every planar graph is four-colorable. And there is also very well-known Gréchy's theorem that tells you that if you additionally forbid triangles, you can improve the number of colors to 3. So both of these are now fairly old results, both planar graphs. And similarly to many other coloring results about planar graphs, these are somehow the basic proofs of these are using discharging method on reducible configurations. For the four-color theorem, it is the only proof that we know, or all the proofs that we know use discharging. For Gréchy's theorem, we now have many different proofs, but kind of the basic one or the first one that was found is using discharging and reducible configurations. And so this is somehow probably the most standard method how to prove something about colorability of planar graphs. And the idea of this method is that you find a number of configurations that you know that can never appear in a minimal counterexample to the statement that you are trying to prove. And then you show that that one of these configurations must necessarily appear in every planar graph or planar graph without triangles or whatever. And then obviously you get a contradiction with the existence of the smallest counterexample. So for example, if we wanted to prove the Gréchy's theorem, then we get some reducible configurations, which for the Gréchy's theorem could let's say be a vertex of degree at most 2, or a cycle of 5 vertices of degree 3, and a couple more configurations like this. And then, well, you do some magic with discharging on planar graphs, by which you show that every planar triangle free graph must contain one of these configurations. And then what you do, okay, so suppose for a contradiction that there is a planar triangle free graph which is not 3-colorable. You take the smallest such graph. By this discharging thing, you find out that, let's say, it contains this 5 cycle of vertices of degree 3. And then what do? You take this 5 cycle inside your graph and remove its vertices and add, let's say, an edge joining these 2 vertices, being very careful so that you don't create a triangle by doing this. So this is not always possible, but you have, let's say here you have 5 possibilities how to set an edge between the neighbors, and one of them always works. And so then you obtain a smaller planar graph, which is triangle free, and therefore it is 3-colorable. And then you show that any three coloring of this rest of the graph extends to a three coloring of the original graph. So it's not a comparison. So let's say this could be colored 1 and 2. I must have different colors because I added an edge here. And then let's say, I don't know, it could be like this, and then you can easily check that you can color, let's say, this way, 5 cycle, and you can easily argue that whatever is the coloring of these 5 vertices, you will be able to extend it as a color of the 5 cycle. And so in this way, you can prove Cauchy's theorem. Okay, so this is kind of for the coloring thing. But here I'm saying something about choosability. So in choosability, we are considering a slightly more general version of coloring, where we are instead of using a fixed set of colors for each vertex, we are at each vertex given a set of colors that we are allowed to use. So, for example, if I could, let's say I want to list an instance of list coloring problem on this graph would be, I am given, let's say, colors 1 and 2 here, 2 and 3 here, 1 and 3 here, 1 and 2 here, and I am asking whether I can properly color this graph, this 4 cycle, such that this vertex has color 1 or 2, this vertex has color 2 or 3, this vertex has color 1 or 3, and this vertex has color 1 or 2. And here I can easily do it. I can put 3 here, 2 here, 1 here, and I just chose the possibility. So it's not so easy. Okay, so I can do it like this. Okay. And okay, so now we say that the graph is k-choosable if it can be properly colored from any assignment of lists of size at least k. So obviously, if a graph is k-choosable, it is also k-colorable, because one possible assignment of colors is that I give each vertex colors 1 up to k, and then coloring from these lists is just ordinary proper coloring using k colors. So then it's a kind of natural question to ask whether we can strengthen these results, whether all planar graphs are 4-choosable, and whether all planar triangle 3 graphs are 3-choosable, and neither of these is true. Margit Voigt constructed counterexamples for both of these things. However, it is true that they that with here with one extra color it is true. Planar graphs are 5-choosable. Here it is also true with one extra color. All planar triangle 3 graphs are 4-choosable, but it's kind of a trivial result. But more interestingly, if in addition to triangles you also forbid 4 cycles, then the graphs are 3-choosable. So if you make planar graphs of girth at least 5, forbidding 4 and 5 cycles, then these graphs are all 3-choosable. And both of these were proved by Thomassen in 1990s. I think this one is 1994, this one is 1995 or something like that. But kind of the interesting thing is that neither of these results is proved by reducible configurations. Both of them are proved using a method developed by Thomassen, where he proves a stronger statement where some of the vertices have even shorter list than you are out here. So let's say you have your planar graphs and vertices on the outer face only have 3 allowed colors, while the vertices inside have 5 allowed colors, and then somehow from the outer face you carefully color things to preserve these invariants. So you show some strengthening of this. And it is open question whether you can prove 5 choosability or 3 choosability of these using some fundamentally different method. Let's say using reducible configurations. And okay, why is this interesting? Well, kind of one reason why to be interested in this is kind of philosophical. You might be asking whether in some sense all things that are true about planar graphs can be proved using reducible configurations, or more somehow what would this mean? I mean, the question is, the formality is raised. The answer is obviously false. You can do some artificial things, but whether in some sense all natural properties of planar graphs follow from some local considerations along the lines of reducible configurations. But more importantly, well, it's always useful to have fundamentally different proofs of one statement, because then some of the proofs may generalize to other settings. So, for example, here generalizing this Thomassen's proof to give coloring results on surfaces other than the sphere. So let's say for graphs on torus is very non-trivial. Recently, Luke Postle was able to kind of do it, but it's very complicated argument. On the other hand, the proofs through reducible configurations typically translate very well to arguments on other surfaces. You typically need to modify a little bit the discharging and maybe add a few more reducible configurations, but things typically go through. Forgetting about what color theorem for it, nothing works, but let's put it aside. So for that reason, it's we were interested, or I were interested, in whether you can prove these two claims via reducible configurations. And for this one, we still don't know. But we were at least able to do it for this one. And in the rest of my talk, I would like to give some ideas that lead to this claim. Okay, first of all, we need to find like good reducible configurations to use in this list coloring argument. And, so here is somehow a basic observation about what you would like to have what you would like to hold for a reducible configuration. So you want it to be somehow subgraph of your graph, which looks in some particular way. It's one of a list of finitely many graphs, and it should have the property that basically if you remove it from the graph and then possibly add some edges like this or some other replacement for it, that still makes the graph girth 5 and smaller, then whatever is the coloring of the thing outside, you will be able to extend it inside as well. And then there is kind of an observation that it's typically not very good if a vertex in your hopeful reducible configuration has more than one neighbor outside. Because if you have here a vertex with two neighbors outside, and okay, it has some list of colors A, B, C, you typically cannot prevent the situation that here you would have, let's say, colors A and B, which force you uniquely to use color C here, and so yeah, so whatever coloring is outside, it basically forces you the color of this or of the vertex. You have no freedom here. So coloring this configuration is pretty much the same as coloring this configuration without this vertex. So yeah, you really don't gain anything by allowing in your reducible configuration vertices which have two neighbors. So somehow the first question that is natural to consider, motivated by this, is whether in each planar graph of girth at least 5, you must be able to find a small induced subgraph such that each vertex of this subgraph has at most one neighbor outside. And such subgraphs are called, let's say, two islands. So, two island is, let's say, okay, induced subgraph or a set of vertices of your graph, such that each vertex has at most one neighbor outside of S. And in general, a K-island would be such a set where each vertex has less than K neighbors outside. So the first question that we will consider is, well, whether in planar graphs of girth 5 we have small two islands. So question, does there exist some number K such that each planar graph of girth at least 5 contains two island size at most K. This is actually known to be true. We proved this with Sergei Norin using argument which is not by discharging. This actually somehow just follows from the fact that planar graphs have sublinear separators, so that each planar graph on n vertices has a balance separator of order at most 2 times square root of n, let's say, and the fact that planar graphs of girth 5 have edge density less than well, average degree substantially less than 4. So from these two facts you can deduce this. And so this is true by this result of myself and Sergei Norin for K roughly on the order of 1000. Okay, so this is nice, but not nice enough, because in order to prove this by reducible configurations, we need to find somehow an explicit list of small graphs that are reducible. So yeah, we could at least in theory go over all possible islands of size at most 1000 and prove that they actually are reducible, but obviously enumerating all planar graphs Girth 5 with at most 1000 vertices is not something that you can do during the lifetime of the universe. So that's not quite what we do. So, and the second caveat here, of course, is that this proof is not by reducible configuration, by discharging. So, kind of this is also somehow again the spirit of what we are doing. But anyway, so somehow mostly this consideration that this doesn't really give us an explicit list of two islands was the main reason we didn't just we couldn't just go with this. So yeah, we thought a little bit about this with Mars Bonamy, Kardos, and Postle, and we find out an argument using discharging, which is significantly better. It only the discharging argument that we go only works under the assumption that minimum degree is at least 3, but that is not a problem, because if you have vertex of degree 2, then it's by itself trivially reducible for three-list coloring, so we don't have to care about this. And then we get this for k at most, probably around 50. I'm not sure. I forgot to count it exactly. But more importantly, we get like an explicit list of explicit finite list of graphs, such that one of them must appear as a two-island in any planar graph of course, at least 5. And then what we do for each graph from this explicit list, we prove that it is reducible for this three-list colorability problem, and therefore we get the proof. Of course, there is a little bit of a problem that this explicit list has some 2000 graphs, so we don't do checking of the reducibility by hand. We wrote a computer to check these things. But okay. We don't. Okay.
25 minutes.
25 minutes. Okay. So there are now two things that I would like to speak a little bit. So first of all, about this discharging argument by which you get these small islands, and secondly, about the way we prove that the configuration is reducible for this problem. And I think actually the second part is more interesting, or at least I'm able to say some more about it. So I will mostly focus on the second part, and if I have a little bit time left, I will speak about the discharging. So how do you prove that something is reducible for list coloring? So that is somehow the most basic thing that we would like to show to be reducible, and that is again this 5 cycle of vertices of degree 3. So this is a very nice one island, two islands. Each vertex has just one neighbor outside, and from some practical considerations of, let's say, the discharging argument and so on, if we were not able to prove that this is reducible, we would be really in trouble, because without, well, it's kind of for the discharging, this is configuration with very low negative charge, and it would be very difficult to account for it in the argument. So we really need this to be reducible. So we can try doing pretty much the same thing we did in the ordinary coloring setting. So we take this configuration, we, for contradiction, assume that it appears in a minimal counterexample. So we have here some planar graph of girths at least 5, in each vertex has list of size 3, and the graph is not colorable from these lists. And we have this configuration. And so now we try removing all the vertices of this configuration and adding edge between two of the neighbors. Again, we need to be a little bit careful that we do not create short cycles. So we need to be careful that this new graph, this edge added, has girths at least 5. But if we are, let's say we are lucky and this is the case. So now, because we consider the minimal counterexample and this has fewer vertices, we know that this graph is colorable from the list that we are given, and it would be enough to take the coloring of this modified graph and extend it to a coloring of these 5 vertices, and if we can do it, then we win. Let's say we have here some nice coloring. Okay, this must have different colors. Let's say we are very lucky and everywhere around we get different colors. And let's say the lists were 1, 6, 7, 2, 6, 7, 3, 6, 7, 4, 6, 7, and 5, 6, 7. And now you see that something is wrong because okay, the coloring of the rest of the graph prevents us from using these colors all except for 6, 7. And so now we are asked to color this 5 cycle using just 2 colors, 6 and 7, and that's obviously not possible, and we are in trouble. So yeah, so actually this reduction failed. And you can try doing different things than just adding this single edge, but pretty much whatever you do, you will be able to construct some bad example which gives you some bad lists, bad colors here, still compatible with whatever you use as a reducer, and then you construct here some bad lists to that you cannot extend. So this kind of doesn't work for this very simple configuration that we would really like to be reducible. Also, there is another problem with this approach. So some of these configurations that we get here have like 50 vertices, and so how would you prove that such a configuration with 50 vertices is reducible? So to do that, you need to show that whatever are the lists assigned to these 50 vertices, from that you maybe subtract some colors according to the colors of the neighbors outside, you still are able to color things from the list. But so to do that, you would have to go over all the possible list assignments to 50 vertices, and that's a very difficult proposition. Like there are again, the number of different ways how to assign lists grows even faster than exponentially with the number of vertices. So there is pretty much no way how to go over so many list assignments. So this direct method of just trying to show that whatever the lists are, you can collect from the lists, doesn't. First of all, it's not strong enough. It doesn't work for this simple configuration. And secondly, probably we would have difficulties in implementing it in practice. So how do we get around this? So we use is a very nice result of Alon and Tarsi. Who gave a sufficient condition for a graph to be list colorable in terms of the graph polynomial of this of the graph. So let's say we have some graph G which with vertex set. Let's say its vertices are integers, so 1, 2, up to n, and then we can define the graph polynomial of G will be a polynomial in variables x1 up to xn, defined as the product over the edges of my graph. Well, let's say I can take the edges so that I is less than j of the difference of the variables corresponding to these vertices. And you see easily that this polynomial has something to do with coloring of your graph, because if you assign any values to these variables, this polynomial will be non-zero exactly if this assignment gives you a proper coloring. Because if this assignment of values is not a proper coloring, you will have an edge that has the same value assigned to each vertex. So let's say we'll have xi as xj, or xi equal to xj for this edge. So this will be 0, and then the whole product will be 0. Conversely, if the assignment of values is proper coloring, then all these differences are non-zero, and the value of the whole polynomial is non-zero. So let's see. So this easily has something to do with graph coloring, and then Alon and Tarsi proved actually the following thing, which is much less trivial, but not too hard to prove, that if this polynomial has some non-zero coefficient, so if it's true that coefficient at x1 to d1, x2 to d2 up to xn to dn in this polynomial is non-zero, then G can be properly colored from any assignment of lists where where x1 is assigned more than d1 colors, x2 is assigned more than d2 colors, and so on. So if you are given any assignment of list of vertices to G, and let's say vertex 1 has at least d1 plus 1 allowed colors, vertex 2 has at least d2 plus 1 allowed colors, and so on, and this coefficient of the graph polynomial is non-zero, then you will always be able to color G from this list assignment. Or since we are only interested in choosability, we can write it this way, that G is the maximum of these d1 and plus 1 choosable. And so,
and you care about L-choosability. So every vertex that's not having a neighbor out has like three colors that it could have.
This is for the whole graph.
You're looking at the whole graph.
Yeah. And okay, so what we would like to prove is that if G is planar, girth at least 5, then there exists some vector of these degrees, d1 up to dn, which is in all coordinates at most 2, such that the coefficient of the graph polynomial of this graph at x to these degrees is non-zero. And then if this is true, then combining this with the Alon and Tarsi theorem, we get that all planar graphs of girth at least 5 are Threechoosable. And now we will prove this via reducible configurations. So let's say what we will prove is that if okay, I have this graph G, and in it I have such a 5-cycle. Let's call this 5-cycle R. It will be our reducible configuration. Let's call this HE. So to prove that this is reducible, we need to show that if I have some D0 vector, which is at most 2 in all coordinates, such that G the coefficient at this in the polynomial of my reduced graph, so G without this cycle plus this HE is non-zero, then from it follows that there exists some other list of degrees such that this coefficient of the graph polynomial of G is non-zero. So if I can show that this is the case, let's say for a 5-cycle, I know that such a 5-cycle of vertices of degree 3 cannot appear in a minimal counterexample to this theorem. Again, the same idea. I take a minimal counterexample. I do this transformation. The transform graph is not a counterexample, so we get that this holds for some d0. But then this implies that I have a good non-zero coefficient in my whole graph, so it actually wasn't a counterexample. Okay, so how do we prove this implication? So, okay, let me call the vertices somehow. So let's these vertices outside P, A, B, C, D, E, and let the corresponding vertices here. Okay, and let G0 be the graph without C, and so okay, we have this assumption that we have some D0 such that x to D0 of this graph, so G0 plus this edge AC is not 0. So this is the same, because well, this polynomial is the polynomial of G0 times xc minus xa. So this is the same as saying that coefficient here 0 xc minus 1 in 0 minus coefficient 0 is not 0. So this is what we have as an assumption here. And now we can try to guess somehow this d that we will use. So one possible guess is that that d could be well obtained from d0, and then somehow we assign the degrees to vertices a, b, and c. So let's say we can have a look at this times x a squared x squared d squared t squared. Let's say there is some motivation for choosing precisely these degrees, but I probably don't have time to go into it. If you think about it, this is a natural possibility. So now the polynomial of g is polynomial of g0 times these extra terms that you get from these 10 edges. So g0 times x b minus x big B, x c minus x big C, and so on, x small b, x small a, and so on. Doesn't matter. It's just an explicit polynomial that you can calculate. And then, okay, so we are interested in the coefficient at this term in the product of these two polynomials. So if you calculate the things, you will realize that this is the same as minus 1 polynomial of g0 minus minus 0 plus or minus. I may the signs alternate, but it may be that what are pluses should be minuses or vice versa. I'm not sure. So up to plus minus it's this. And well, this is still not still cannot derive anything from this. But then you can also have a look at this coefficient. It's a squared, it's b squared, it's c, it's d squared, it's e squared using polynomial, and again up to plus minus signs, you will get that this is so SP inverse the same thing with SP inverse plus A inverse minus XB inverse. And now I claim that one of these two coefficients must be non-zero, because if both of them are 0, then also their sum is 0, or difference is 0, but depending whether I have here pluses or minuses, which I don't know. But here these two differ exactly in that here I have the term x with xc inverse here, which is not here, and here I have this term with xa inverse. So the difference of these two coefficients, so if I take this minus this, or plus this depending on the signs, is precisely this coefficient, this thing. So because the difference of these two things is this, and by assumptions this is non-zero, we get that one of these coefficients is non-zero.
All the things that are inverse are capital letters.
Yes.
Okay.
Yeah, sorry. All these should be capital letters.
Confused that you divided by something
Yeah,
that's not in the polynomial.
Sorry about that, my mistake. Yeah.
Yeah.
All these letters here should be capital. And yeah, so from this we are able to show that this is a reducible configuration. So this seemed like a lot of magic, but actually it's not all that bad. As I told you, there is some method for why I guess that I should be looking at exactly these coefficients, and then this computation. So I can do it, basically do this computation for all the possible things that make sense here. This gives me some linear combination of coefficients similar to this, and so then I am just trying to say if all these coefficients happen to be 0, then this must be 0. So I'm just saying that this linear combination is linearly dependent on these linear combinations, and then so that's just some trivial linear algebra to solve. So with fairly reasonable amount of computational power, you can verify automatically whether the configuration is reducible or not, and that's about the end of my talk.
Thanks, Zdeněk. Questions? Is there some general picture how the configurations look like? Or
Kind of. Okay. So so we have things which we call half islands. Half islands are kind of chains of faces which are incident with exactly two vertices of degree 4 and vertices of degree 3, which can be somehow attached to each other according to a couple of rules, and then it ends at a face which has just one vertex of degree 4 and all other vertices of degree 3. So you have, we only take these half islands with let's say at most 4 faces, and then such an half island can then attach to some central face. So let's say one possible reducible configuration that we have is this one, where on this edge I have another half island, and on this edge I have attached another half island. So it's basically like these chains of faces with exactly two vertices of degree 4 linked together to some central vertex, so which kind of ensures now that each vertex has at most one neighbor outside of this configuration. And then we have, let's say, I guess maybe 15 possibilities for how such a half island can look like, and in the worst case we have one central face on which we have 3 half islands attached, which then combines to, let's say, these hundreds of thousands of reducible configurations, but all of them look kind of similar. So
this must look a lot of linear algebra things like this.
Yeah.
So going from the smaller polynomial to the larger polynomial doesn't, as far as I can tell, it doesn't seem to give any picture of how to extend the coloring from the small to the large.
Exactly.
That's
the big problem of this Alon and Tarsi method, that it will tell you yes, it's colorable from all lists of the size, but it gives you absolutely no guidance how to actually find the coloring. And as far as I know, there is no known algorithmic way how to.
Well, I think what you have there is more or less a counterexample to that hope. This picture.
In a sense, we sort of believe that there is another way how to go about reducing the configurations using so-called correspondence coloring, which is another further generalization of list coloring, which has the advantage that it really works very similar to the list coloring. So we will be able to explicitly extend the colorings. But then we run into this problem with the configurations being actually too large to be somehow straightforwardly able to show that they are reducible for this correspondence coloring. So we haven't explored it very completely, but I sort of hope that it might be possible to push this through in this direction, and then we would actually get an algorithm. No, so far this is just purely existential development.
More questions? Let's thank Zdeněk again.